In this RC Revolt post, we are experimenting with printed TPU tire inserts. This was designed to mimic our preferred dual stage foam setup, and it's actually a tricky problem to solve from an engineering point of view. Our goals were to get as much initial compliance or softness out of the insert as possible, but also to have a stop point after about half the compression stroke to prevent excessive wrinkling in the tire, or worse, a complete collapse that will upset the balance, dynamically move the CG around, and resulting in the losing of that planted car. Also challenging is the fact that we really only want compression longitudinally, not laterally, meaning if it easily compresses with force applied at the shoulder of the tire, it can roll under while side hilling. With our taller 4.75 Hyrax, the ones we like on our rocks, this roll under is a real problem with the stock included memory foam. Now, your mileage may vary with your rig, terrain, or tire height. We've tried a few other 3D printed designs previously, and they didn't pan out so well. We found that they either didn't have enough early compliance, they were far too rigid when first pushing on them, or it was just a shape that didn't lend itself to FDM printing.
Yeah, buddy, that was cool.
This design features a ring of concentric circles that only like to be compressed in one direction. They intersect at points, creating arcs to one another for the entirety of the radius around the wheel. To get our stop point, a compression stopper, those circles are kept from compressing with a skirt that traps it, making a taper down to the wheel interface. But the real light bulb moment came from looking at wall thickness. What we found was that we needed to design the walls to be approximately equal to our extruder's nozzle. Understand that in FDM printing, the nozzle size is also a variable. Most popular is the 0.4 millimeter, but you can go as low as 0.2 or as high as 0.8, depending on your application. Matching this variable to the object design eliminates any, we'll call it noise, when the slicer software builds the G-code from the shape. We found that we could tell the slicer our nozzle size and print just one thin wall where we wanted it. If this matches the object, you get a predictable amount of compression dampening. Thus, if we want a firmer or softer insert, we scale the wall thickness of the object up or down and change the extruder nozzle to match. And there is some play here. For example, if you are printing with a 0.6 millimeter nozzle to extrude walls that are 0.72 thickness, you can tell the slicer to extrude more material. However, if you want walls that are 1 millimeter thick from a 0.4 millimeter nozzle, the slicer just adds a second or third wall layer, and we found that this increases the rigidity of the print in ways that are really hard to predict. Even more complex is when printing an object that someone else drafted, and they had a different printer setup in mind when they created their object. So both of these rigs were custom built, and they are inspired by West Desert Wheeler. They are Gspeed TGH V3 carbon fiber chassis, and they're running Fusion motors through a Stealth X transmission and a low-range flip kit. They have various other 3D printed parts like bumpers, radio and battery box, and a tweaked rock slider design that I'm quite proud of. They both have a forward weight bias of around 54% and a total weight of a little more than 6 pounds. We've got 1 year crawling on these, and they have done just outstanding for us. I can do a build overview video if anyone's interested in looking at this setup. But the footage today is from 2 separate outings. The first one is about 65 degrees and dry. The second one's about 55 degrees and very wet. While we built them together, there are a couple of differences in the setups. Minor suspension tweaks in driving style will cause delta here. The same line, the same car, the same driver, two different results. We acknowledge that happens. A sample size of one isn't a compelling story. However, because we're engineers who know better, we're also testing more than one variable at a time, right? So the red car is wearing Hyrax in Predator compound, and the green car is wearing Hyrax in the G8 compound from Proline. Now, this is a real thing. You can go to Proline's website, and they have what they call an application guide. And it points out that Predator is intended for wet conditions below 60 degrees. G8 is intended for warmer, drier applications. With our experience and these two runs, we pretty much confirmed that, yeah, Proline knows what they're talking about. The softer Predator compound found more grip in the cooler weather, especially when it got wet.
So these are G8s. Mine were Predators.
We also know from summer runs that as the temps rise, the softer Predator compound loses grip compared to the G8 compound. Now, as far as TPU inserts go, one assumption that we were able to validate is that TPU inserts withstand water infiltration much better than foams. Our tires are vented along the outside, and the footage shows, if you look closely, they were submerged and ran with water filling that tire. So, from our experience with foams, this much water would definitely compromise that soft memory foam layer of the dual stage insert, and it would cause degradation in the foam in as little as one run. The biggest unknown and untested assumption about TPU inserts for us, though, is longevity. We only have about 3 packs run on these, and initially they look good, really good. But as our design goal was to replicate something like the Proline Dual Stage foams that we know and love, we're going to have to run these for at least a season, and in some of our hot 100 plus degrees days to get a good data set. When you consider that the insert is basically a damper or shock absorber, and that cyclic compression count, as that cyclic compression count rises, there's going to be a degradation in the material, just like wet foam inserts. That degradation will cause the TPU part to become softer. So that leaves us with this. With these variables, number of walls, wall thickness, and the brand of the TPU, the initial compliance goal we hit, our desired amount of softness. And they emulate the performance from our dual stage foams very well with that stop point. Now, we acknowledge that can and probably will change with temperature and time. But the beauty is that printing these ourselves, we can revisit any of these variables as the season progresses. We also have the ability to tune these prints to our application. For example, a firmer insert could be used in the rear to support a heavier rig, while having a soft front insert to aid that lighter front end when it's climbing. A thicker print could also be used in a trailing application where durability is more of a concern. And finally, this brings us to the economics of TPU inserts. Let's forget the cost of the machine, the design time, print time, electricity, etc. These are actually quite cheap to make. I also enjoy building objects for use in the RC hobby, so we'll call it a wash there. I already had the machine. I do recommend a direct drive and a heated glass bed for TPU, by the way. But the particular TPU brand used here is Duramic, and it's a cheaper one found on Amazon. I paid $45 for 2 kilograms, or 4.4 pounds for the barbarians like me. And I can print almost 38 pairs of inserts with that material investment. That works out to less than $1.20 a pair. When you compare that to the $25 for a pair of dual stage foam, that leaves a lot of incentive for us to experiment and replicate. I'll leave you with that. Thanks for watching RC Revolt.